Hello everyone. So I'm here to present the paper Enhancing Fault Location on Transmission Lines by combining travel and wave-based functions available in real device. This is a paper that was written in partnership with several colleagues, so I use my time to present the paper, but here you can see the name of all of them. We know that when a transmission line fault takes place, travel and waves are launched from the fault toward the terminals of the line, and we can detect the first instant wavefronts or even reflections or refractions of these wavefronts in order to calculate the fault distance from a given reference terminal, which we are calling here local terminal. If you would like to calculate the fault distance by using one terminal data, there's no need for time synchronization. But if you use two terminal data or multiple terminals, data taken from multiple terminals, synchronization means would be necessary. The problem arises when some time synchronization error takes place or when there are uncertainties in the settings used to calculate the fault distance. And these settings usually are based on the propagation velocity of the line, which is a characteristic parameter. Sometimes we use the line travel time, sometimes we have to use the transmission line length. And these uncertainties in these parameters can lead the fault locator to present errors. Here, this figure illustrates, for instance, when we have a time synchronization error, it seems that we are applying like an offset over the time here in the travel wave detections on the remote terminal. In this terminal, we do not have errors because this is the reference terminal. And when there are uncertainties in the propagation velocity, for instance, the waves can be faster or slower than we expect to be. So it also can result in errors. So when we consider the traditional fault location methods, the traditional formulas used to locate faults, always if you have uncertainties in time synchronization or in the fault location settings, always we will have an ideal estimation superposed by an error term. And in this case, we can see from these formulas that the higher these uncertainties, the greater is the error, such that reducing the influence of these inaccuracies in propagation velocity or even in the time synchronization, it is very welcome to enhanced fault location procedures. So the proposed solution here is a practical solution, in my opinion, which consists in combining promptly available results taken from real device that use the traditional double-ended and the traditional single-ended travel wave-based fault location methods. You do not have to calculate to implement algorithms to detect travel waves. This task will be performed by the relays in the field or the DFRs, so you can take the final results and combine them to have an enhanced fault location result. This is the most important contribution here. And by doing so, we are expecting to compensate errors in time synchronization and uncertainties in the travel and wave propagation velocity. Just to summarize here, you can see further details in the paper, but usually off-the-shelf device use these formulas here, which are the double-ended and the single-ended travel and wave-based fault location formulas. And basically, which are proposing is to add to this hall of methods two other methods that we have published previously. You can find these solutions in detail in these papers here. But basically, one combines only the single-ended travel and wave fault location taken from both line terminals in order to compensate the effects of uncertainties in the propagation velocity and time synchronization errors. Or you can use the second approach here, which cancels the effects of uncertainties in the propagation velocity. So the main idea is basically you read the results from the real device, and firstly you ask, okay, are synchronization means activated? You can take these informations from some word bits which are usually available in relays and DFRs. If so, if the the synchronization means are activated and operating as expected, we enter in a second question. Are single-winded traveling wave fault location methods available in at least one terminal? If so, you can take the one terminal to terminal distance estimations and the settings that you programmed in your device, and you can take all this information here and use that formula that I presented in the previous slide in order to cancel the effects of the propagation velocity. Otherwise, probably you would prefer to use the traditional two-terminal method, which basically would be applied here using these parameters. But if the synchronization means are not activated, the traditional two-terminal method cannot be used. So we enter in another question here, and we ask, are single-winded traveling wave fault location methods available in both line ends? If so, you can use that other solution that I presented to you, which will combine only single-winded methods at both line ends, canceling the effects of time synchronization errors and also in propagation velocities. Otherwise, you will have no other choice unless the use of the traditional single-winded approach. To evaluate this approach, we tested real and simulated case, 4 real cases in which the fault distances were validated in the field, and 2 simulated cases using the alternative transients program. But all the records were taken from the simulations or from the database of real case, and they were played back in real device in order to make the test more realistic. We know that the traditional range of propagation velocities can vary from 97 to 99%, but we decided to extrapolate it because we know that people may commit some errors during the parameterization of the device, the fault locating device. And basically the unsynchronized case were obtained by just removing the communication channel and disabling the GPS antennas from the tested device. Here is the summary of the results, and I will go forward for the results. In the first case, we have CG fault. It's a short line, so the time difference between the first wavefronts at both line ends is very short, so it reduces the effects of uncertainties in propagation velocity. But we can see that when we use the single-ended approach here, if you commit some errors in the propagation velocity setting, errors can reach the order of 1.2 kilometers, but the proposed method remains with errors that did not exceed something like 100 meters, for instance. But we see that the double-ended method is okay, because as I mentioned, the time difference between the wavefronts is very small, and it limits the effects of uncertainties in propagation velocity. But when we consider a longer line and far end fault, for instance, we can see that the double-ended and single-ended traditional approach, they may reach errors of dozens of kilometers, whereas the proposed method remains here with very low errors, irrespective of the propagation velocity setting used in the approach. The final result is another fault in a long line, and we have almost the same behavior of the traditional techniques, whereas the proposed method remains with very accurate results. So, as conclusions, the presented methodology indeed enhances the traveling wave fault location procedures. We consider that combining results, promptly available results from traditional double-ended and single-ended fault location methods is practical, is easy to apply because you do not have to implement algorithms, and it will reduce the effects of propagation velocity uncertainties and time synchronization errors. Real and simulated cases were evaluated, the proposed methodology was validated, and the obtained results showed that the solution is indeed promising. The maximum error did not exceed 563 meters in the case, both simulated and real case, whereas the classical methods presented errors of tens of kilometers in most advanced cases. I'm not telling you that using traditional methods is bad, it's good, these methods are good, but sometimes we have to think differently, and this is our proposal to enhance the fault location procedures. Okay, thank you very much for your attention.